Thank you very much, Lisa. So, okay, it's my pleasure to give kind of the seminar, which is like a tutorial about machine learning and its application. So actually, this tutorial actually assume you have zero knowledge about machine learning. But if you do, please bear with me, okay? So I try to tell people up from scratch about those kind of machine learning essentials and ABC, okay? No technical stuff in today's lecture. If you are interested in that, after today's seminar, you could talk to me, okay? We can talk about a lot about technical details, okay? First of all, I would let you know what is called machine learning. So basically, machine learning is kind of the underpinning technology for build up the intelligent system, so which is also closely relevant to another subject, which is math and statistics. This is a cross-discipline area. So basically, if you want to build up something today's called intelligent system, that means some machine try to mimic humans to do something with humans' behavior, intelligent behavior. So basically, if you want to build out those kind of system, then you need equip those machines with those kind of intelligence. So you can imagine what kind of intelligence we have, right? Like at very beginning, we have eyes, we have ears, we can listen, we can hear, we can also watch. Then eventually, we can understand what we see, right? So basically, those kind of things, computer vision, and those kind of speech or oral communication functionalities. So basically of that, actually machine learning provide a kind of technology actually try to help you to carry out those kind of the functionalities. So this is directly relevant to machine learning in many, many areas of AI. Some kind of thing called data mining, you might maybe heard of that. If you never heard of that, it's something, give a bunch of data, whether or not you can find some kind of information which make data sensible or meaningful, okay? So basically, machine learning is directly associated with those kind of area. But some kind of area, they could related to the artificial intelligence like robotics. Actually, robotics is a quite comprehensive subject. So for the body part, actually definitely it has nothing to do with machine learning, it's mechanics, right? And others, dynamics. So basically machine learning can offer those kind of brain to the robots, right? So basically machine learning are indirectly related to those kind of the areas. So also machine learning down to the earth, in essence, eventually when we solve the machine learning problem, we always convert those kind of problem into math problem. Then use math tools, in particular in those kind of statistics, use those kind of traditional methodology in one new math tools to solve those kind of problem. Basically, it is a kind of technology for the AI, but we rely on the math to solve the problem. Okay, this is machine learning. So you would be interested, what is most salient feature of the machine learning? So machine learning has one single and unique feature called the data-driven problem-solving methodology. So why we call it data-driven problem, data-driven nature? Basically, without the data, without machine learning. Or you say, I have no data, can you apply machine learning to my problem? I would say, no, no way to do that. So machine learning 100% relies on the data. So the methodology, according to Tom Mitchell, this is a well-known machine learning inventor, probably the terminology, the modern machine learning coined by this guy called Tom Mitchell in the CMU, College Mellon University, in 1996. He wrote the first textbook called Machine Learning. In that textbook, he summarized the methodology of the machine learning as it's a methodology, machine learning is a methodology which make a computer learn from experience. Now, given a task, then the machine learning would get at better, make the system get better with the experience. Nowadays, we no longer call that kind of thing as experience. We call the experience actually encoded in those kind of training data. Like data is a carrier. All the experience must be encoded or reflected in the data. So now, that's why I said, we have to learn from the data. Previously, they called from experience. But in general, this kind of machine learning has 2 steps or 2 stages if you want machine learning system works. The first one we call the training process. So basically, we have to get some kind of the machine learning model, and we must get training data related to one specific task. You define a task. I will give you a few examples after that. So given a one task, then those kind of machine learning model in layman language, like you have some kind of the system. System can behave within some kind of capacity. System can do everything. But if you want to make a system to solve your specific problem, there are a lot of controlled variables in that system. Okay, we call it parameters. Then the learning process is how can we use the training data or experience to tuning those kind of parameters. Eventually, when the parameter get into the proper values or fix that model got trained. So in order to train that model, we normally define our learning goals as some kind of the math form called the object function. Right? Once you get the object function, it will tell you how good, how bad so far you finish the given task based on the experience. Right? So when we try to get the proper parameters, actually in terms of mathematics, is amount to you try to do the optimization based on that object function. Right? You try to tune that. Eventually, based on those kind of optimization process or procedure, eventually you will find the proper parameters. Then you fix that. By then we say we already finished the training phase or training stage. We got some learned model or trained model. Then everybody here, if you use something like fingerprint recognition or face recognition, all those models already trained. It's the next stage. We release the model to application user. You can use as designed, right? So this is the general things you need to know about how machine learning works in very general. But in machine learning, there is another feature, very, very important. It's quite different from all others. In other words, you would ask, what is the ultimate goal for any machine learning system? I would say, remember one word, that's enough, called generalization. What generalization means? So basically, machine learning is going to build up a system which try to do something beyond those kind of training data or seen subject or objects. For example, let's say we do some kind of face recognition. So we have to get the training data like people's face for individual face. Actually, from different angles, you take pictures, people's face looks quite different, right? So actually, when we try to collect training data, we only collect 1 or 2 from some specific angle. We never ever collect from 360 degrees to every kind of things. So eventually, we use 2 pictures. We build up this model. Actually, the model is expected to recognize you from any angle. That means machine learning is not going to memorize those kind of the training data or information you have in those kind of training data or scene data. We want the system always work to unseen stuff. If you cannot do that, it's not machine learning. It's some kind of memory. Machine learning is not a memory system. Machine learning is a system which can handle the similar things, but quite different. Actually, in essence, it's quite different. So I'll give you a few examples for when we approach to the details. Well, like human, we can make machine learn something in different styles. This is my taxonomy. So normally there are only 4, actually. Basically, first of all, what kind of style machine learning can have? Basically, in my taxonomy, I have 4 different paradigms. Traditionally, only 3, first 3. But I will tell you why I add 1 more, okay? So basically, the supervised learning, unsupervised learning, reinforcement learning, and emerging learning is my terminology. Also, under each learning style, there are some kind of generic learning tasks. This is not specific task. It's some kind of scenario you can work. So I will one by one to let you know what of the rules. Okay. First of all, let's take a look at the learning paradigms. Just a different kind of learning style. The first one is supervised learning. Supervised learning also called teachers, some kind of teachers-based learning. So basically the idea is you given some kind of the data, you want to do something, which is we know the goal. Based on those kind of examples, we know exactly the ground truth. So all such kind of thing, if you have the data in this kind of format, the training example in this form, either the raw data or some kind of feature extracted from that data, plus the ground truth, which is a goal you want to do. So basically, those kind of supervised learning can be used to many kind of the applications. First of all, the prediction. I'll give you an example for the prediction. The prediction, like we try to predict the stock share next day, tomorrow, or next week. Like this is the example for the Amazon. So in this case, actually, the input data, actually the raw data or features, is those kind of historic stock share values. It depends on the window size, 1 year, 3 year, 5 year, or 1 month, whatever. So basically, you have that. Maybe plus some other factors. One day, whether or not there are some kind of earthquake or blah, blah, right? So anyway, those kind of things called data. But because this is historic data, we know the ground truth. Like Amazon, yesterday, the 1 share is actually just say 10 pounds, right? 10 pounds. We know the value. This is ground truth, right? So eventually, we use those kind of data. This is the kind of things. You must have those kind of the input plus those kind of the ground truth. That eventually, we can train a model. Once the model, as I said, you got the proper parameters, then model fixed, right? Then you can input tomorrow's up to today's data to predict tomorrow's value. Okay? So this is called prediction. The second one is normally scenario is a recognition. Many kind of recognition, I just said. Let's say the object recognition. Object means everything in the pictures. Here, we have different objects. Human, we treat it as objects, okay? Like a human, dog, animal, and a car, vehicles. So basically, the idea is for our training example, if you want to build up those kind of the object recognition system, we expect we have the training example like this. The raw data or feature must be those kind of pictures. Pictures must have those kind of either human, dog, or animal, and the cars. Plus, it's an ID, the human label, and the dog label, and that label, okay? So if you collect a bunch of the kind of images, we will train a system. Then eventually, when the learning system is done, then you can use that to recognize new people. Maybe me here is not definitely from those kind of parents totally different, right? So, but we still can say this is a person, this is a people. Then another kind of dog, another kind of dog. Also, you can imagine the medical diagnosis. Here for a doctor is like work at a doctor. How a doctor can diagnose a disease? Basically, they have to collect those kind of symptoms. And with some kind of test result, have some kind of measure to test, blood tests, blah, blah tests. Put them together, then do some kind of inference then doctor said, oh, you suffer from what kind of disease, right? So this is a process. Same thing here. If you want to build up the machine learning medical diagnosis system, so you need to collect those kind of patient profile. Those patients must be already diagnosed correctly, normally, right? From those kind of profile, from those kind of archive, you can find those kind of profile about the patient and the diagnosis results. So basically, you still need to have two parts. Those kind of profile is describe the patient's symptom and testing result, and the decision, the ground truth, right? So basically, if you got those kind of data, you can do a lot of things. Because most of you come from social science, right? So I'm going to find some kind of concrete example from social science. Unfortunately, very few. I found one. It's quite successful. It's a very new one, actually. It's the last couple of years. But this is a project, it's a joint project among 3 universities, Harvard, Cornell, and Stanford University. They built up a system called the pre-trial decision-making system. Okay, that system, you know the pre-trial issues for court, right? So you have a defendant, then before you have a trial in the court, then judge have to decide whether or not to keep you in jail or allow you to stay home, right? So that kind of decision you have to make based on a lot of factors, at least whether or not, if the guy outside the jail, whether or not he recommit some kind of new crime, right? Something like that, many factors. So based on that, actually, they have a data set. They collect data of 1 million those kind of court cases for some kind of bailed or jailed cases. Then based on that, in this case, actually training example is those kind of the profile about each previous defendant, what kind of crime he suspect to commit, right? Age, gender, blah, blah, whatever you can find from there, descript those kind of the defendant. What is the decision made by a judge? Maybe different judge, which judge? Oh, okay. Basically, you have those kind of two informations. One information is actually those kind of defendant personal information, and the other is judge decision. You have the two piece of things, two jigsaws. Then this is supervised learning. Then you use those kind of the data, then you can train a machine learning model. So eventually, when you finish that, you will get a model. When a new case coming, instead you use a judge to analyze those kind of profile to make the decision. The system can automatically make a decision, jail or bail. Okay, so that is something. So this is some kind of the social impact. Now, basically, in the last year, actually, because it's a system built up in probably 2015. In the 2016, according to the technical report, they said the jail of up to 42% fewer people without increased crime rate at all, right? So at that year, I think in that year, actually, there are 12 million people arrested. Not every year, probably. I don't know. I cannot remember what exact situation, but this is some kind of impact. They say machine learning definitely can make impact in those kind of social problems. Okay, this is one successful story so far I can find for the social science. So very few examples there. Okay, this is supervised learning. So second learning paradigm is called unsupervised learning. It's just like humans. So the supervised learning, like we were very young, maybe before the school age or just the primary school age, teachers say, give something, you should do this, yes or no. But later on, when we grow up, we have the capability to do something without the teacher help you. So basically, in this case, we no longer have a teacher. We no longer have a teacher, that means we no longer have those kind of ground truth. But sometimes we want to use that to discover something even human beings do not know, okay? So basically, in this case, the training data would be just those kind of raw data or features of the data. Feature means given those kind of the original sensors input, you might do some processing to get some features, okay, depend on the system. Like image, you could only use the image pixel-based one, we call the raw data. You could already use some kind of edge detection algorithm to get those kind of edge, object edge. Start from there, we call the feature. But all those kind of things, we call that as input data. But in this case, in supervised learning, we have a ground truth, right? Now we no longer have a ground truth. But this kind of the learning style can handle those kind of the real problems. The first one, you can automatically extract salient features to describe the object better than raw data. For example, if we want to do the face recognition like humans, we never ever check every bit on your face, which scan, whether or not there's a spot on your skin or something. Normally, we just focus on those kind of salient characteristic of your morphological structure, right? Your eyes, your nose, or something. So basically, you could apply those kind of technique to those kind of face data, the raw data, and eventually they give you some kind of data, some kind of the features. This is those kind of face. It's a very famous term in the face recognition called eigenface. So basically, they give a small set of those kind of eigenfaces. Then every people's face can combine it, linearly combined with those kind of face. In other words, with those kind of the face, we call the basis face, any face can reconstruct from there. We just need a small number of that. Normally it's less than 50, that kind of things. That means if we have those kind of the eigenfaces, then for any pictures here, at the moment, you know, the size of the picture is very large because we have the high resolution, right? So normally, we have several million pixels here. If you handle that kind of thing, it's very difficult. You could use this way to convert original more than 1 million pixels into 50 numbers. The 50 number is good enough to represent the previous face. Okay, so this is the first thing you can do. Second thing is probably more intuitive. So basically, in many, many areas, we want to find how similar those kind of objects look like, how similar those objects behaves. So in this case, the unsupervised learning can handle something called the clustering analysis. Basically, they can automatically grouping those kind of objects of some kind of coherent property. If they are similar, in other words, if they are similar, they put into one group. If they are dissimilar, they put into different groups. Okay? So this is another typical application of unsupervised learning. The third one is some kind of a latent factor analysis. Maybe it's probably very important in the social science. So basically, on the surface, we've got a lot of data. But the useful information in the data is quite limited. For example, this is our own applications. So basically, now I'm collaborating with a medical school colleagues. We try to find from the kind of cancers patients' DNA, whether or not we can find what segment of DNA contribute to a specific cancer. Right? Those kind of DNA sequence for each people is more than 20 millions. Not all those kind of the DNA pieces contribute to the one kind of the disease. Only some kind of level, but it's hidden here. Nobody knows. Even human beings do not know this. Then, whether or not, also sometimes, not only one segment, maybe more than one segment, they related together, occurred to cause this kind of disease. So this kind of things actually also unsupervised learning algorithm now also working on those kind of problem, but it's still in the young age, okay? But we have a try to do something like that. I try to find something closer, relatively closer to social science. There is one example, maybe it's interesting, but I don't know 100%, not like those kind of pre-trial decision making. It's definitely a social problem, but I don't know whether or not it's a social problem. yeah, now that there is some kind of research called digital artist. So basically, use the unsupervised learning, you can transfer some kind of unseen image, new image, any kind of image, with a given style. What that means, for example, this is a very famous painting by some artist, okay? So then you got those kind of nature picture to take from anywhere, right? So eventually, through the learning, then you can convert a picture from the original nature picture to those kind of painting with the same style. Even the style itself is hard to describe and specify. Just say, oh, like this style, but you cannot say what exact style is, right? As long as you have those kind of painting, like Van Gogh's painting, and those kind of nature images, we just use this data, we can do those kind of style transfer. So here's a few examples. You have these pictures, given this kind of the style, painting style, it can convert into here. Like look like this, I cannot describe accurately. If you give this kind of style, the picture becomes here. Then you give this style, become here. So on and so forth. It's 5 examples. Actually, this kind of the technique, this is the first paper address this issue, right? So there are follow-up. The follow-up is try to extend those kind of the method to actually to convert one nature pictures based on other pictures you could call the style, you could call those kind of the lighting conditions to convert from one to the other. Suppose we have those kind of original picture. Then you say, I want to see the night view of the pictures. You don't have to wait to the dark. So eventually you get another picture actually different from here, right? So definitely quite different in different city. It's the night view. Then you give that 2 pictures, actually the system will generate. The picture is a night view of this city. These skyscrapers, okay? So this is another example. So if you want to get this kind of style, then you give this picture, then eventually that picture become this kind of looking. Also, this is another example. If you give those kind of purple river scenery, then you give this kind of a picture with some kind of sunshine or something. So eventually you will get that kind of things. You can say, if you, now, so in this case, actually, we try to use those kind of machine learning system to learn some kind of styles. Eventually, we can convert and generate new data or those kind of virtual data in some kind of the area, maybe useful like film making, movie making or something. You don't have to exactly to get that kind of the things to take a picture. It's quite expensive, it saves a lot of money. I don't know other kind of potential, but at least it's quite amazing. We can do something which is we can generate whatever we want. Even something is hard to describe. Okay, so this is another examples in the unsupervised learning. The third one called reinforcement learning. The reinforcement learning actually is quite different from the other 2. Basically, we could call that reinforcement learning as the goal-oriented learning through the interaction with the environment. So basically, it's like an animal learning style. I'll give you an example here. So basically, if we put a mouse in some kind of maze, then put some food in some kind of cell or some kind of room of the maze. The maze consists of different room with some kind of layout, sometimes complicated, some kind of simple. Then mouse maybe have some kind of the nose, they can smell the food. They try to get the food to eat. Then the mouse have to try to get the exit or door of each room. Then find the right path from the room the mouse located to the room there is food, right? So basically, this kind of process, it depends on the environment, right? You have different maze. Maybe the path looks like different. You put the food in different room, the path also different. A lot of things is very, very hard to tell people, say, you must go through exact path to get that food. There is a style that actually reinforcement learning allow you to do something I call a trial and a test. If I don't know that, I can try. So basically, if you try, if you walk on toward this direction, you will hit the wall. That means there isn't a door there. Then you got a penalty, right? So then if you get the right direction, you find the door. You move, you turn up, then move toward that direction. You get out from this room to another room, maybe closer to that food. So then, basically, each time you will get those kind of penalty or reward in a certain environment. Okay, so eventually, by trying different room with those kind of feedback, either penalty or a word, or reward, then you might find that kind of path. Eventually, those kind of past experience were included in the mind to help you. Next time, you get quicker to find a new path. So this kind of thing is called reinforcement learning. So in general, this is not only for the animal, actually for any kind of robotics. If you want that do something in some very complicated environment, normally we start with this kind of style. To let the robot, like if you try to teach the robot to walk, the robot must stand up first, and probably just take first step, a second step. But sometimes it's very hard. This time, the rule is free, I can go. But if you move the table a little bit, it blocks me, right? It's very hard to tell robot everything. Robot will try. If they hit the table, means no way there. They have to turn up, turn around. So basically, with this kind of ideas, that you can teach those kind of agents to get familiar with the environment, to do something which is hard to give those kind of ground truth. Okay, so most successful stories, probably this is the first successful story is a human human is beaten by the machine, which is a checker, American checker, in the early 1980s. Later on, actually, for the text poker machine learning system already better than humans, right? So this is use this pure reinforcement learning. You can gradually improve those kind of skill to some kind of level. So this is all three traditional machine learning paradigms. Okay, it's quite traditional. But nowadays, machine learning progress rapidly, in particular in last decade. So there are many new learning paradigms. Normally, we try to have some kind of smart combination between those kind of learning paradigms. Sometimes not exactly 1 + 1. Sometimes you have to have the you have to be fused deeply with something I call the emergent learning paradigms. For example, nowadays not everybody, most of you maybe heard of the term called the deep learning, right? What's deep learning? Actually, deep learning on conceptual level is nothing new. It's a neural network. But why we call it deep learning? Because this guy, Jeffrey Hinton, he proposed some kind of training algorithm to train a neural network with a new learning paradigm, in the new learning paradigm, which is combining those kind of unsupervised learning and the supervised learning, make those kind of training process much simpler. Then he coined the neural network or neural computation as deep learning in 2006 paper. So now everybody call that as deep learning, actually neural network. Even for myself, this year, exactly 30 years, I study neural networks, right? So only such kind of subtle difference you can distinguish between neural network and the current deep learning. Of course, new stuff add on, but in essence, it's all neural networks in the deep learning. The second one, actually, nowadays is quite popular learning paradigms in many areas called semi-supervised learning. So in words, probably you can guess the meaning. The idea is actually when we train a system with a supervised learning paradigm, within those kind of paradigm, you normally need a lot of training data Do you still remember what kind of format of the supervised learning training data? You need to have those kind of the input data which describe the object. You need the ground truth. Where ground truth come from? It either come from the expert annotation or come from what already happened, right? But for some area, it's pretty hard to have those kind of label data. For example, if nowadays we try to forbid those kind of atom bomb test, right? So basically, atom bomb test definitely affect environment, right? So if you say what kind of real or actual environment affect, you just can based on, you only can based on the previous test data. Sometimes it's a state secret, right? So it's very hard to get those kind of label we call the ground truth. In this case, actually, nowadays there are a lot of those kind of atomic reaction test, maybe in some kind of the power station or something. You still can collect some kind of data with not that scale, right? But we don't have those kind of the effect labels, but we still have a lot of those kind of atomic reaction data. So we could use that together to build up a system which still can predict the impact of those kind of atom bomb. So this is maybe it's a very extreme case. The idea is actually you just need to use very limited annotated data, labeled data. In particular, the labeling is laborious, time-consuming, very expensive. Then you use a lot of unlabeled data without those kind of labels. Then put them together, then you can build a system to get the performance as good as you use a lot of data to train, a lot of annotated data to train a system. So this is quite new, relatively new learning paradigms. In last 3 years, this kind of the combination make a great impact. The supervised plus reinforcement learning. I believe most of you heard this story, AlphaGo, right? The Go is probably the ancient board game invented by the Chinese. Actually, probably the most difficult board game. People 3 years ago, nobody would imagine in the next 2 decades, machine can beat the human expert. But actually, now machine already far better than the humans, AlphaGo. Basically, AlphaGo actually try to adopt the supervised learning plus reinforcement learning, put them together to get that kind of performance. The supervised learning still rely on the human experts, the game, what kind of policy used, with the policy, how much winning rate it got, okay? Based on that, to train the initial one. Then because it's a machine, you could copy the current program into another, like a player A and player B, let them self-play. Then with those kind of the value, those kind of evaluation to know whether which policy is better than which. You eventually put them together. Second one is reinforcement. They don't know which one is good. They try a different move in the policy, right? Different policies. Then that one you play. Because there's a clear rule, we know win or loss, right? So eventually they use that kind of reward or penalty eventually to improve the scale. So merge them together or combine them together, you can quickly make the system learn something. It's hard to learn. Also, nowadays, actually, probably in the next few years, if there isn't ethical issues, we won't need to learn how to drive cars because those technique for self-driving vehicles are already there. It's quite mature. Just because there isn't those kind of lawful issues, those kind of lawful issues not settled, so that's nobody can use that or not allowed to use in the real world. So actually, one of the technique they used to identify people, try to make the those kind of obstacle avoidance is a new style. It's supervised plus reinforcement learning. Okay, this is something just like. Okay, this is some kind of the learning styles. Actually, within each learning styles, you could face different kind of the learning task. This is general learning task, not from the application perspective, actually from machine learning perspectives. So sometimes we call the learning task as offline or online. It's quite traditional. Offline is actually, let's just use the supervised learning examples. On one time, we have all those kind of annotated data. It means we have all the training data once. Then we can use all the training data to train the system, then to get something. So sometimes that kind of annotated data is hard to get once. You have to gradually get it. Or some kind of data nature, like stream data, right? The time series, the data just bit by bit coming, right? So whether or not you don't have to wait, you collect enough data. You start from the first data coming, then you start learning. So this kind of task depend on the data, depend on the real requirement. You could have the offline data if you have enough training data already. Or you could start learning even without enough data, but we gradually add the data. So this is called offline and online tasks. Okay? Next one, we have a passive and active learning. The passive learning is probably all the first thing I mentioned. If you give those kind of the data description, the raw data, plus those kind of ground truth, those kind of training data together, then it's a passive learning because things are already there. But sometimes people want to save the time because for the supervised learning, you must give the ground truth. Ground truth given is a labeling process. So when you collect data, we don't separate the data collection and the learning. Instead, the expert try to look at those kind of data, only label most important data. Then once get data, we immediately learn it. This is like this kind of loop. Once you found data, you are not sure whether important or not important. Yeah, give the system, in particular, if you use online learning style, then they give you feedback, say, oh, this data is good. Okay, this kind of data is more important than others, or less important. Then you will give you hints to find another data you need to get that. In this kind of case, we call that kind of style as active learning, which can save time and try to get the most important data. So it depends on those kind of training data availability and the annotation process. Now, there are many, this is the two traditional ones. Those kind of things only appeared in last 5 years. This is called emerging learning tasks driven by the real requirement. The first one, a very odd term called zero-shot learning. So actually, zero-shot learning is a kind of the things. You don't have to collect all the data, training data, but it still can do something beyond that. Okay. Typical example is fruit recognition. So when you first collect data, probably you just collect 5 kind of the fruits, for example, apple, pineapple, blah, blah. You forgot to collect the pear. Another thing looks like an apple, right? So whether or not you could use those kind of the attributes of the two types of the fruit, we call it semantic correlations, to use the current system to recognize the pair. Even the pair data is not used. Pair image never ever appear in your training data. So this kind of thing called zero-shot learning. Also, we have the transfer learning. Transfer learning means we already built up one system. Then when you try to build another system, normally you have to start, as I said, you have to start from everything from scratch. Whether or not you can use this kind of system to take some kind of knowledge, transfer to the other, then make that system train faster. Multitask learning. So far, 90% of learning system only can do one thing. If the face recognizer only can recognize face, cannot recognize anything else. So basically, whether or not you can let one learning system to learn multiple tasks together, multiple things together to do the multitask. That even extended to this is called lifelong learning. It's very new kind of the task. The idea is actually, when you first, like humans, when we learn one task, somehow we not only can perform on this task, but also we already abstract some kind of knowledge. If next task coming, we learn a new task, like you play football, then next one is rugby. It looks very, very different, but some kind of skills, like running, for example, a simple one, right? So they could be transferred, right? Basically, once you have one, but the other coming, you can learn that very quickly without damage those kind of skills you already learned. Okay, so gradually you can learn many, just exactly like human, right? Learn how to learn. So this is kind of things for some kind of new terminology called artificial general intelligence. So nowadays, the current artificial intelligence system we call narrow. Why? Because it only can handle one task normally. Now we want to let that handle multiple tasks. Then this is probably about those kind of ABC of the machine learning. Okay, so because most of you probably may not be interested in how to study those kind of topics, right? You're interested in how to apply one kind of machine learning technique to my problem, to your problem, whatever problem. I don't know your problem, but I try to use one data set. Everybody can understand. It's easy because we have the very sophisticated visual system. Okay, so now let's give you demonstrate what's the generic methodology for application. So basically, as you can see, I think everybody can recognize, it's a set of the visual images, right? You have a different people, right? So basically, first, if you do the applications, you have to formulate your problem accurately, then convert it into corresponding machine learning problem. Some people say, oh, I know my problem. But for most, according to my experience, most of application users do not know their problem accurately. They just roughly know the problem. For example, from this set of data, how many kind of the task we can formulate, how many kind of problem we can formulate. First is easy. You say, oh, face recognition, because this image collected from different individuals. Of course, if we want to use face to authenticate people, ID, then we could use that data to do face recognition, right? Yes, right? So second one is, I'm not interested in that. Actually, my research topic is about, I'm just interested in no matter who. I want to know at the moment or when the picture was taken, what's your expression? What's your mood? Whether or not you're happy, what's your emotion state? In this case, actually, even we have visual images, but the visual images need different kinds. Because first face recognition, you need for each individual to collect those kind of the face images, one or two. Right? Tell this kind of visual image belong to Lisa or belong to me, right? This is called ground truth, right? Then give those kind of data to system can train that. It's a supervised learning. Second one, also the supervised learning, but you need to have a different kind of data. In this case, we don't care about who, we care about at the moment, if you give me one visual image, what is the emotional state? Right? Like here, the guy smile, no matter it's Harry or somebody else. That means you have to collect the data with different emotion state. We don't care about from you, from him, right? So basically, this is totally different things. Then we need different annotation or different labels. So this is quite obvious two tasks. You could ask me whether or not you can figure out any more problems from this data set. Yes, a lot. For example, whether or not you can predict the age of the person in that data set. Eventually, you build a system. When you show a pictures, the system will tell you you are 38, you are 46. Whether or not, yes, indeed. If you want to do this problem, we still need those kind of the data set. But we need different label. Meaning, these are all the supervised learning. Whether or not you can figure out there is any problem belonging to the unsupervised learning, yes, I can. Basically, I could, with the people, we could say, who looks like who? So how similar two people? It's very hard to give some kind of golden criterion, say, based on these criteria, they are similar. So basically, you just can roughly say, oh, it looks similar. So basically, unsupervised learning, well, discovering those kind of the similarity relationship between people is unsupervised. Even we don't know how many groups, given those kind of different peoples, we even don't know how many groups are there. So each group of people should look very similar. If people in the different group, they must dissimilar, right? So we don't know that, but machine learning can help you do something. So basically, down to the earth, when you have the problem, maybe from your angle, you think you know the problem. Then from machine learning angle, we have to discuss together to see what kind of learning paradigm is. Supervised, unsupervised, reinforcement learning may be more complicated. We have to somehow combining 2 or 3 learning paradigms. What kind of a task? Whether or not the data bit by bit coming, or at the beginning we get every data, right? So it's kind of like the online, offline, right? Whether or not the data is very hard to collect it, whether we need to do some kind of semi-supervised learning and some kind of zero-shot learning. So all need to discuss those kind of application user and machine learning practitioner might be work together to first define the problem properly, formally properly. Then also you should have some kind of realistic goals. Machine learning is a kind of the mechanical system or whatever system. It could make mistake. Actually, it often make mistake. In other words, we couldn't get error-free performance normally. So you have to assume when the error making, what happens, whether or not this error accepted, whether or not we need some prevention method. Say, in this case, we put it uncertain. We don't use machine learning system. Instead, we use some kind of human to do some kind of intervention, right? So basically, those kind of the goals you have to set when you build up some applications. So this is not in order, but sometimes you say, because why I collaborate with you? Because I already got a big data set. But in this case, you don't have to do the collection. So in this case, you just need to think about, so far the data is good enough, or is good enough in terms of quality, is enough to have enough amount data for machine learning. So if you don't have those kind of data, probably you have to consider how to collect the data required for the machine learning to build up the machine learning system. So after those kind of things, this is the multiple round interactions. So we will do the next one. Next one is, as I said, once we determine the learning paradigm, we just define that. Once we determine generic learning task, we define that. Actually, even we fix that, for each task, there are a lot of different learning models with different capacity and strengths and weakness. So how can you choose that? So for example, nowadays, maybe people could easily to identify something called deep learning and shallow learning. Yeah, maybe this is not right taxonomy for machine learning, but as people easy to understand that. So it's totally different learning models. Actually, how to choose that? Whether or not deep learning always the first choice, actually not. Okay, basically something like that. Once you decided the proper learning model, we have to train with the proper learning algorithm. Sometimes we have to build up some kind of baseline. The baseline tells you whether or not the model select is proper, like a cross-reference. So after you finish this kind of training, you have to have some kind of performance evaluation. You have to do the performance evaluation properly. Sometimes you have to compare with the baseline. It's another loop, multiple round loop. So eventually you believe the goal, you better goal set already carry out, you can release your system to users. Okay, so probably this is all about machine learning and application in non-technical style to give you. So just take 1 minute, I just let you know. I have multiple slides, I just use one slide here. So actually I'm running a lab called machine learning perception. So actually I'm doing the research in both fundamental research in machine learning and with some kind of application area. So my principle is actually I look at those kind of fundamental problem in perception, like either vision and auditory system, whether they are common. Then I try to use that to think about whether or not the existing machine learning method can handle that. If they can handle that, is not my research target. Then if I cannot find a machine learning method to deal with that, I will study machine learning. Then eventually I demonstrate on those kind of problems. So those kind of problems actually are the demonstration area of mine. But sometimes, occasionally, if I got some kind of proper collaboration, I work beyond that. Like from last year, I collaborated with a colleague in medical school. We try to automatically find the motif from DNA sequence. Yeah, just let's just jump to from those concrete examples. So let me spend minutes to conclude the seminar. So basically, machine learning nowadays gradually becoming an emerging technology to solve the real problem in different areas, right? So, but actually, people expected it's easy to use, but unfortunately, for most of the kids, if you just download some kind of toolkits that apply to your data, normally it doesn't work. Why? Just because people do not understand the proper things in machine learning. As I said, based on the taxonomy, you have the learning paradigm. You have this kind of generic learning tasks. Even you fix that, you still have a different model to choose. Each different model has different properties. So how can you do this? Basically, it also depends on the understanding of the machine learning. Means it's real collaborations. We need domain knowledge plus machine learning expertise. Because most of your guys work in the social science, I try to figure out whether or not there are something we can do together. So basically, I believe actually machine learning can do something. At the moment, social scientists didn't do that. Basically, at least this is for the causal inference. Probably it's a very common problem in the social science. You want to know the cause. Actually, now we have some kind of models. If you have a big data set, we can help you to predict those kind of counterfactuals. Okay, so sometimes it's very hard for humans to analyze the big data set. The next one is probably you can automatically find the complex correlations on those kind of larger data set. Nowadays, if you just use a very simple one from the statistics, they just can find something on surface, not in depth. Also, based on that, you could automatically generate some kind of hypothesis. You don't have to apply theory, apply some kind of the handcrafted stuff to generate the hypothesis. So also you can break those kind of constraints of existing theory. This is so far, because I know relatively little about social science, this is my view about that. So my lab definitely is happy to collaborate with those colleagues to solve the real world problem. Okay, thank you very much for your attention. Yeah.